nothing. Okay, so let's get started. It's 10:15 in my clock.
You haven't started doing the stream yet?
I thought I did.
Or maybe it's just delayed. No, no.
Okay. So here's sort of the plan for today. We'll sort of finish up on distributed linear algebra, the main primitives for representing matrices across machines. And then I will, as promised, I'll get back into this power plant pipeline. So in this example, we will go beyond the, the understanding of the business case and exploring the data and go into model building and tuning and evaluating the model. We'll do everything except deployment. And also we will get into both linear regression and two kinds of ensemble methods on trees. So one would be gradient boosted trees, so we'll sort of see at a high level what these things are. And then in this other example, which I like, it's this talk from last year from a big data conference in Europe. And this one's about activity recognition using accelerometer read measurements from cell phones, whether you're sitting, walking, jumping. Then we'll use another ensemble method for trees called random forests. Okay, that should be. So you have to, I guess, upload data from. Upload the archive, the latest archive. And let's see. Space. So this guy. Okay, so this. Okay, so so the paper I was sort of looking for last time is here. This is from the archive. Matrix computations and optimizations in Apache Spark. This is the paper last year. I strongly recommend sort of looking at this if you're interested in, especially improving the algorithms or really understanding what's happening under the hood. So this is quite good. Let's see. So section 2 is essentially what I will just quickly cover. And this talks about various representations of distributed matrices, the row matrix, index row matrix, coordinate matrix, block matrix, and so on. And how this representation is useful for various matrix operations. Again, it's beyond the scope of this course, but I just wanted to get you guys plugged in if you want to go into it. So I think in extra resources, if you go to linear algebra programming guide, and then the machine learning programming guide, I believe we have, I just started putting this stuff in. So, so you can kind of get a feeling for, we went through the local objects last time, so let's go into, how you would be using this basic data type. So yeah, I have some errors. Sorry, I'll fix this. Oh yeah, it's because my yeah, I'm using an old version of the SDS thing. So let me just fix this quickly. So I need to delete this, and I need to quickly import this should be fine. So okay, so I mean, I don't want to go too much into this because we simply won't have time in this course. But some of you may want to know what's really happening under the hood. Okay, so so if you want to do projects, we can revisit this later. But just know that you can start directly manipulating these structures if you need to. Okay, so. Okay, so let me quickly get back to here. So let's start with this power plant pipeline. And okay, so one thing we want to be able to do is you know, essentially call the other notebook that did the first 4 steps from this notebook, right? So for that, we want to do this run command, and assuming you put the directories in the right place, you should just be able to run this command. And there is an annoying thing with Databricks Notebook. So before you run the command, please delete the cell. Otherwise, it just is going to create 2 copies of this, basically. Okay, so then you should be able to just run this command, and this will call that entire notebook that we did, right? The 009 notebook, which should be in Scalable Data Science, SDS22, this notebook. So let's try that. Should take a few seconds, and then we'll start getting into data preparation, modeling, and tuning. So maybe I'll just start here. Okay. So yeah, this is a pretty big notebook. So let me know when it's finished on the community edition. So I think the last cell won't really work in a reasonable amount of time in the community edition, but that's okay. So this is our basic data set. So now we want to basically be able to do data preparation. And for that, let's see if the schema is available. Here, oh, it's still running. Okay. Yeah, so my master student is running some job in this community cluster, so pretty much tied. So let's see. Let's hope this works on time. Okay, so let me just quickly tell you what we're going to be doing here, right? So I'm going to print the schema because the table has been registered, and then I'm going to essentially, have this vector assembler. So we want to be able to take these four as the input column. This is the temperature, atmospheric pressure, relative humidity, and vacuum. And then we want to set the output columns to be features. So it just basically takes these four columns and turns it into a vector. So that's what the vector assembler does. And then what we want to do is do linear regression, but with some penalization, right? So this is using the ridge regression idea. To be able to do this, we want to split the data into training data and validation data. So we can do this random split method. So it'll just take some seed and split it into 20% and 80%. Okay, so then that's what this would be. So then we simply just look at the counts so that we actually cache the test and training data in memory. So now that'll be cached, and then I can take just 3 elements of the data set just to see what it is for the test and the training and the actual data set. And then for linear regression, we have these imports. So we want to import linear regression model, and the pipeline. And this will create our linear regression object, LR. And this gives us all the various parameters that are in it. And finally here, we're going to set up our pipeline. So we're saying set the prediction column to be predicted _ PE. So this is what the model will predict fitting. And the label column is PE because this is a regression, right? So we want the power output. And these are just some other parameters for the gradient descent. So maximum number of iterations is this, and I'm now setting the regularization parameter to be 0.1. So this is the regularization parameter that came with ridge regression. You know, if you remember from Amit's video. So this regularization parameter is what you multiply the coefficients by, right? Because the idea was that the larger the coefficient, the bad it is. So we want the coefficients to be small. So this in the ridge regression, this regularization parameter will penalize the models with very large coefficients, right? So that's the idea here. So, and then I'm essentially taking my LR pipeline, setting the stages, and for the stages, I just need an array that tells me the steps in the pipeline. So I have my vectorizer and then my linear regression model for these settings. Right? So this will give me my LR model finally by simply calling this pipeline with the .fit method. And then of course I have to put the training data set as input into it. So the training data set gets vectorized and then turned into this LR model, and then it gets fit. Okay, so this is just the mechanics. And we saw the basic theory behind linear regression. It's just fitting hyperplanes, so 2 dimensions. We did a simulation with the blog from Darren's. So Darren just generated a whole bunch of points, x1 and x2 on the plane, and then put some known intercept and slopes and fitted some with some errors. He fitted some value y's. And so in just a two-dimensional regression, x1, x2, all we have is a plane. We lift it to some intercept b0, and then we use the slope for this axis, which is b1, and then for given b1, you have something like this, and then you maybe use the other axis slope b2, right? So it's just a hyperplane. It's a standard hyperplane in 2 dimensions. Of course, in higher dimensions, it's just hard to visualize, but it's a linear model. Okay, and then finally, you can fit and then get the intercept and the weights after the fitting has been done. So in this example, this is what the intercept and the weights were. And then we can simply find out what the columns were that were used as the explanatory variables, simply all the columns except the power output. And then I'm, sort of just zipping these things, just produce this formula here. So I can ignore all this, and in the end, all I'm doing is simply getting my linear regression in this sort of equation form, right? So I have y equals the intercept minus the slope for AT, minus the slope for V, and the slope for RH, and so on. Okay. So, okay, and then you can sort of look at this. What did we exactly do? So we took these 4 columns and tried to predict PE, and the linear regression gives us the predicted PE. So this is actually where the hyperplane is, right? So this would be a hyperplane in 4 dimensions. So then if we do a difference between PE and predicted PE, we get an idea of how good the fit is. Right? So that's the other main step. So for that, we use the evaluation evaluators with the regression metrics. So now you can say my metric is, okay, so it's the predicted PE and the PE. So these are my 2 columns I'm selecting. And then I simply do an RDD, and then I map this to the 2 doubles. So if I use that as my input, an RDD of the prediction and the actual value, then I can use that to initialize my regression metric object. So then you can ask, once you've done this, then you can ask various performance metrics. You can ask what's the root mean square error between the predicted value and the true value. So that's RMSE. So this would be, after the fit, it's 4.6. You can get at other things like explain variance and R squared and so on. So these are different. So depending on what the underlying model is, you will have various performance metrics that are natural. So in the end, we sort of have this explanation, the best fit is given by, say, root mean square error. So we can compare this linear regression against something else like random forest or gradient boosted trees we're about to do, because these values like the root mean square error are comparable across model families. Okay, so here the story is for a regression, you would expect approximately 68% of predictions to be within 1 root mean square error, and 95% of the predictions to be within 2 root mean square error values, right? So this is basically a simple sanity check of how good your regression is, and that's exactly what this is just implementing. So we can simply use the select expression method and say we're interested in the actual power output, the predicted power output. The difference between the actual and the predicted as residual error. So we take the absolute difference, so not the actual difference as the residual error. And then we simply, so this is nice method. So I'm actually saying this is a string, except I'm substituting in column values from outside. So I can say I'm interested in the residual error divided by the RMSE, and I want to know, I want to label that as within RMSE. So then if I evaluate it, what I'm able to get is just this expression in SQL. So I get the actual output, the predicted output, the residual error, and whether it's within the root mean square error or not. So then you can simply plot this and look at what the within RMSE values are distributed, how they're distributed. And we can ask, is it within absolute value 1 and 95% within absolute value 2? And once again, you can just do a SQL statement for this. And it looks like it's pretty reasonable, right? So 67% is within absolute value of 1 of the root mean square error, and over 95% is within 2. So this is just saying that the regression is doing quite good. It's not a bad fit, basically. So then step 7 is very important. So now we want to make sure that we're doing some kind of tuning. So try to keep a lot of this manageable, but I'm not sure if this is going to work in the community edition yet, so I'm trying it out. So what I'm going to now do is the parameter grid builder. So we did this before for the tree case, I think. And then I'm also going to use the cross validator. So cross validator is now this abstraction that allows you to do cross validation for tuning hyperparameters. So cross validation is very similar to just doing a random split of the data into validation and test set, except in cross validation you would essentially repeat it many times, not just one random split, but you would say say 5-fold cross validation, you would divide the data into 80% and 20%, and then this 20% could be actually now varying 5 different times in the data. Okay, so you average over different subsets of the data. That's the idea of cross validation. So it's more robust than just doing a random split. Okay, but it's also more expensive. So what we can do is now have our regression evaluator to be to have the power output as one of the columns, and the predicted power output to be the set prediction column. And then we can set a metric name to be RMSE. So now we sort of define this regression evaluator object. And then now what we're going to do is create a cross validator. So just take a new cross validator, and then we set the estimator to be the linear regression pipeline model. So we can, the nice thing with this is we can just change the pipeline model to some other decision tree pipeline model down the road, and not go and mess with the cross validator, for example. And here the number of folds in cross validation is 3-fold cross validation. So essentially it'll repeat the training and validation sets 3 times. And then the evaluator, I'm going to just create the regression evaluator, which is the one I just defined here with the root mean square error. Yeah?
Do you do this on the training set because you already split your data set?
Yeah, no, that was for that was a different thing we just did earlier. So I'm now doing, yeah, yeah. So this is so that's a good question. So we should. Sorry, I'm just maybe going too fast. So let's see. We should.
Because I mean, at the very beginning, we put this 20.
Yeah. No, absolutely. So that's different. So right. So. Yeah. See, when I did the split 80-20, I fixed the regularization parameter to be 0.1 or something, right? Now I'm actually going to, in my parameter grid, I'm allowing the regularization parameter, I will be allowing the regularization parameter to take different values. Okay, so I'm coming up with a very different splitting scheme. In fact, it's not a splitting scheme, so it's a good question. So let's just actually look here. Okay. So let's see. So we have string. Let's see. Classification and regression. So let's see. Missing the. I think there was a link further down, maybe. Give me a sec. Yeah, so there's two ways to do this, right? So one is to do the split, and the other one is, oh, I think it's this one. Let's see. Yeah. Yeah, so, okay, so we have you know, these sort of standard ways for doing hyperparameter tuning. So one is using cross-validation, and the other one is this training validation split, right? So this is kind of what we've been doing. Where you simply split the data into a training and validation set and go forward. But the other one is, and this is good for, well, this is all you can do if the data set is really, really large and you really don't have the gas or the resources to do a proper cross-validation, because it's, you would do this, right? But if you want to be able to, if you have enough resources, and it's much better to do cross-validation because you're sort of taking an average over multiple passes through the data, right? So this is the other way of doing it.
But why is it exclusive? I mean, because I can actually still like having your validation state apart, but then still you have your training set, and then you can do cross-validation with someone on the training set. Because you're still
okay, so maybe I should say, okay, let's just be, let me just quickly tell you what's, let's just, okay, so here's my data set, right? So one thing I can do is just, well, this is a random split, okay, so okay, let's do this properly. So suppose I have data, this is 1, 2, and so on, these are my rows. Really, okay, I have data points, so these are my rows. So what I'm basically saying in the random split method, what are we doing? We basically do, we basically toss a coin. Actually, we're doing permutation. So we would permute all of this, and then take after the permutation. So maybe this is 3, maybe this is 11, this is n, this is 1, and so on, right? After the permutation, I would basically take the floor or the ceiling of n times, say, 80%, right? So the index running from 1 up to this, I would take as my training data in the split method, right? And the remaining permuted indices, right? The remaining 20%, I would call that test data, okay? So that's your very simple two-way split, or you can even split it 3 ways. You can say, oh, I want whatever, 60% to be training, and then some validation, and then some test, right? That's just one cut. What's different about cross-validation is that you play this game over and over. So the simplest way, so let's just keep it as a two-way split, just training and test. So then in a threefold cross-validation, for example, what you'd be doing is maybe you will, use, after the permutation, you will use this for training and then this for testing, right? Except you do it 3 times. You would, play this and then take the rest as your training and the second one as your testing, and then you do it 3 times and then you take the average of it.
Yeah, but then I mean, this I understood it.
Yeah.
Because you split every time and then you reshuffle.
Yeah.
But then I was thinking you would tend to overtune quite a lot. Because I mean you create a model, you validate it, you recreate a model, you validate it.
Yeah.
Then it would be reversed, but then it would still be good to have a test set separate, which is not known from the cross-validation system. Just to really evaluate the performance of your model. Because in a sense, you store all the data.
Yeah. I mean, I don't really. Okay, maybe I'm not following your question. All I'm saying is, when cross-validation is just a multi-pass version of the usual split, right? It's because in the usual split, you lose. I mean, you're bound to this random choice, right? You just, why should I? Because you have a pseudo-random stream, and it's deciding what the permutation is, and then the last 20% or whatever, right? That's a kind of an arbitrary choice. So in cross-validation, the idea is to get rid of that randomness by averaging, basically.
Yeah, but
you see,
the final, so you do this cross-validation and then in the end average or something to get a better model.
Yeah.
This in some way still assisting in constructing the model.
Yeah.
But I guess what you mean is in the final evaluation, right? Like of the final model
Yeah.
after you do the
Yeah.
cross-validation. That evaluation is done on a completely different.
Yeah. Sorry. Okay. Yeah. So you have test. Okay. So if you want to think, yeah. So you have training. So I was just, training, validation, and then of course test is separate, right? So
Before.
Yeah. So
yeah, that's what I have.
yeah. Sorry. Yeah. So that's a separate. Yeah. Okay, so, but the problem is cross-validation is good theoretically, but it's expensive in practice. So we cannot really do this all the time. Right? Okay, so let's go back here. So, I mean, so the point here is this, Apache Spark lets you do all of this in parallel. So your parameter grid builder and the cross-validator, they're all trying to take advantage of your distributed, structures under the hood, right? So that's, okay, so let's see. Okay, so, you can change this to however you want, and then you're doing threefold cross-validation, and so here's the regularization parameter, right? This is the lambda times the size of the gradient, the coefficients themselves, right? So if this number is 0, remember it's the standard least squares. But if this number increases, then the penalty keeps increasing, right? So we don't know what should be the optimal value for this regularization parameter. So it's called the hyperparameter. And we're essentially using cross-validation to tune it, right? So we basically try different values of lambda, and then we can see how well this value of lambda does against the validation data that the model is not allowed to see, right? So that's what this part is. So then I'll just create some 10 values, and then set up this parameter grid builder, and then all I do is crossval.fit and then pump in the training set. So the training set goes through this cross-validator, and essentially it does the fitting. So it'll produce the model with the best hyperparameter in terms of the mean square error that we set. So anyway, this is just mechanics, but the point is you can do this for large data sets. Okay, so and then here all I'm doing is just finding out what the RMSE is, the root mean square error is, right? And so the root mean square is 4.5, and in this example, I don't think we gained a lot by playing around with the hyperparameter, because the one I just chose to be 0.1, I just magically chose it because I chose the best one and put it there. So, but if you didn't know what was the right hyperparameter, then this will help. Okay, so then what I wanted to mainly convey in this is try to have two different models come from completely different families sort of fight for best prediction. And so that's what this one is. So we already saw decision trees a couple weeks ago. So now what we are going to do is use the decision tree classifier, regressor here. So remember when we saw the decision tree for the handwritten digit classification problem, we used the string indexer and converted the prediction, the label column into strings, right? Because they were discrete digits. Here we want the power output to be a continuous variable, so we're going to use decision trees for regression, right? The only difference conceptually is that now when your decision tree goes and starts cutting stuff and creating these simple functions, your height, or, the y value is going to be coming from the mean, the average of all the different y values in that cell. Okay, so that's kind of the main difference. So once again, with this, I'm setting the prediction column to be predicted PE, the label column to be the power output PE, and the features to be the features column. It's the same input. So max bins is just a parameter. It's the coarsening parameter. How many discrete bins am I going to project my continuous measurements into? And you can play with that as a hyperparameter if you want. So and then I'm setting up my new pipeline here and set the stages to be the decision tree classifier we just defined and the vectorizer. So the vectorizer is what's going to create your features vector. So if you just feed in the data into the pipeline, then all of this should work. Now the beauty is crossval was something we already defined for the regression, right? So we can simply use the same crossval and just change the estimator, which is the model, to the decision tree pipeline. So this is kind of the main punchline. So you should not do a lot of time redoing everything, and you should just interchangeably plug in chart basically different models. So then now I for the parameter grid builder, I actually want it to be the right hyperparameters of interest. So I'm using the max depth of the tree itself, right? Maximum depth 2 or 3 as my parameter of interest, hyperparameter of interest in the grid. And then the crossval set estimator params map gets changed to my param grid for this decision tree problem. This is the only other thing I've changed. Right? So my crossval object is still the same. So which means I'm still going to use the root mean square error for my metric, my performance metric. So here, all I have to do now is my best decision tree model will be simply crossval.fit to my training set. Okay, so looks exactly the same as the linear regression case, except now we made sure that the hyperparameters are the depth and what else did we change? Yeah, I guess that's the only thing we changed. Okay, so so then when after fitting it took about 19 seconds, you can get the debug string output of the final tree. So this is basically you find the best model as instance of the pipeline model, stages. So it's the last stage, and then you simply ask if there's a debug string, and then it'll tell you what feature was split on to the left and the right, and so of course you can just see that as a picture here. So these are just the feature columns. So it's just simply split different features, and then it's giving you the power output, average power output in those leaf cells. Okay. So that's decision tree for regression, and then so the question is, how does the decision tree model compare to our linear regression model? then you can simply do this. You can take the best model from your decision tree and then transform it using the test set, which the model hasn't seen. And right, and because remember, this is from the original split, we kept it aside. And then this is essentially what we're getting for the predictions. So we want to be able to compare this. So I'm simply finding out what the root mean square error is here. And that's all I'm basically printing. So what's, if you recall, the decision tree's root mean square error is actually worse than the linear regression. Linear regression was around 4.6. Decision tree is around 5.2. And there'll be slight variations in this depending on the randomization. So anyway, this doesn't mean decision tree is bad. It means maybe it's not rich enough, right? Because we only allowed a couple depths, and there's only one tree, one best tree. And we did tune over, max depths, but what we could go for next is an ensemble method, right? Which is now going to allow not just one decision tree, but a whole forest of trees, a whole bunch of trees to explain the same thing. So these are very popular methods still. So I think we should maybe spend a little bit of time on the two main methods. So one is the gradient boosted one, and the other one is random forest. So let's quickly look at this. So this is something people should be learning in a standard machine learning course, right? Is this something you'll learn, right? But it doesn't matter if you don't learn that. We can learn now. It's not, the idea is very simple. You already know intuitively what a decision tree is. We did it with the San Francisco, New York example. So now the extra twist is we're going to use not just one tree, but a whole sequence of trees. So the idea is something like this. You first, so you're trying to explain this function, this continuous translucent density. That's what you're trying to capture using a tree. So here with just a tree with one depth, you get that kind of fit. With two depths, you get, so you basically are increasing the complexity of the simple function, the partitions in the simple function that approximate it, right? So this is one tree. So now what we want to be, so this is just to, so here is how the tree is built. So you try to find splits that are optimal, and you want to try to use simple functions to minimize the mean square error when you're doing this. So in gradient boosted trees, the idea is now you combine not just maybe 100 decision trees together. And the way you do that is, so if you sort of look at this, essentially by using lots of trees, you're able to have a much finer fit, basically. Okay, that's the main idea. But the way you do it is actually in this following sense. So you first try to fit fit the tree. So fit the function with one tree, and then you would try to use the new tree to fit the residual, what you couldn't fit with all the trees up to now. So it's this, the basic idea is, so dfx is now given by the 3 trees you have so far, and then the fourth tree will actually try to fit the difference between the actual function f(x) and the decision up to the ensemble up to now. So it will always just, the new tree will try to fit the residual, and then the next tree will try to fit the residual that's left unexplained by all the trees up to now. Okay? And the nice thing now is you can use trees with shallow depth and allow them to specialize their partitions completely differently, right? So that's the power of this method. So anyway, you can sort of see this. I mean, you should really implement this to understand this, right? But for this course, it's enough to just sort of abstract out some of the details. So now the gradient boosted regression tree is implemented in Apache Spark. So here is, very standard settings for this. So I just again have to choose my label column, what I want my prediction column to be named, and then of course I have my features, which will be these vectors that we've already ready to transform. I set some seed, and then I can choose this to be my my sort of discretization level, and then this is the number of iterations in my gradient descent algorithm. Okay, so, and then my pipeline is same as before. I have my vectorizer, which produces features from the input columns, and my GBT, which is the gradient boosted regression tree. And I take my same crossval and I set my estimator to be the GBT pipeline. And my Paranal Grid now is going to be, again, I'm playing with the max depths that are allowed in the tree, just a couple of them. Unfortunately, this will take quite a long time to fit. And in the end, this fit will be way, way better. Okay, so I actually ran out of heap space this morning when I was trying to implement this, because the academic shard is quite busy, right? So what? So this would basically produce an ensemble of 120 trees with the depth of 3, and the performance prediction will be way better. Okay. So that's just an example of playing with 2 classes of regression methods, and choosing and tuning each one using its own hyperparameters, and then choosing the best one using the root mean square error. Right? This is a standard thing you'll be doing in data science. Okay, and the point here is this is super simple if you use the machine learning pipelines. Okay, so did anyone try to run this? It's not working, or
it took 5 minutes.
5 minutes.
Yeah.
Okay. Wow. Right. Well, yeah, it's free. So, and if you can run this one, it'll be nice to know, like, when this finishes, maybe after Fika. It should take maybe 15 minutes or more. But,
Isn't it, I mean, this gradient boosted trees, if you always then, when you add another tree, basically deal with whatever is still wrong.
Yes, exactly.
Isn't there a like big worry that you would overfit?
Yeah, that's definitely the case, right? So that's why we're still doing. So I think here the number of trees can be used as a hyperparameter. Yeah. But of course, you're always holding some back in your final test. At least in this one, it's a fair fight, right?
Because I guess if you're adding trees long enough, you should always get to the point where you make no mistake.
Yeah, absolutely. You will fit everything. You'll saturate it. That's right. Right. Just like even the classifier example we saw, right? So we want to play with the maximal depth for sure. So I used that as one of the parameters. So in the validation, in the cross-validation phase, it'll try to fight that, right?
It's somehow it feels that this is more dangerous than just using a few trees and then using rotating or whatever.
Yeah, it's more dangerous, I guess. But but you want to. I mean, generally you will have quite a lot of data, right? And so you would want your models to get richer. But you definitely have to make sure they're not overfitting, right? So as long as you do something like cross-validation to correct for it and use the right hyperparameters in the cross-validation scheme, which at least is maximal depth. And in fact, here we should use maximal depth as well as the total number of trees being used as well. I mean, I just already at 15 minutes. But yeah, that's what you would do. Good question. Yeah, so I don't know if some of you have, if you haven't seen gradient boosted trees and things like this, it may be you haven't. Well, that sucks. We should have Fika. So yeah, some of this may be too far out, but it's okay. You know, you come back to it. It'll make sense. You know, and then we'll come back after Fika and do this this other thing back to derecognition. This is more fun.